Welcome to episode 103 of the Live with the Maverick podcast. The theme for today's discussion is deep learning, and we are very excited to have with us a return guest, Ron Richman. Ron is a qualified actuary and insurtech founder who is a thought leader in the actuarial data science movement. So welcome back, Ron.
It's a real pleasure to be here, and thanks for having me back on the show.
Very excited to have you back, and honestly, we've had maybe one or two. I think you may be the third repeat guest, and we only have back guests when I know there's lots of great potential for content, and just really appreciate some of the things you're doing in the profession, helping to modernize, and all the research papers you're doing, and we're going to have a chance to showcase some of those later. So just very excited to have you here.
Likewise, great to be here.
Great. So just love to give you an opportunity to introduce yourself.
So, Dom, like you mentioned, I'm Ron Richman. I am an actuary with a very significant interest in how the profession can modernize, how we can do things better. I've been in the P&C part of insurance for about 17 years now, held various different roles from chief actuary most recently at Old Mutual Insure before I stepped out to do something entrepreneurial. Before that, I was within the AIG group where I was chief actuary and chief risk officer for their Africa entities. So I've had a pretty good view of actuarial practice as it pertains to property and casualty insurance. And hopefully some of those insights that I've garnered over the years, we can share here today.
Yes, I'm looking forward to exploring those, and you have a very multifaceted background as you've spoken to. And before we get into the details, I mentioned in the intro, and you just mentioned that you recently started a new entrepreneurial venture in insurtech. So how would you describe this venture?
Thanks, Dom, for the opportunity to discuss it a little bit. So I'm now about almost 2 weeks into this new venture, so things are becoming a little bit more defined as the time passes. Basically, as I think we're going to discuss in the rest of this episode, I've had this real interest in applying AI, applying deep learning and techniques from machine learning to a lot of actuarial practices. And what I hope we'll do within this insurtech is provide some software to actuaries who'd like to be able to exploit this more obviously and more easily within their day-to-day work, and also provide consulting in some of these themes. So I think this union between actuarial science and some of these modern technologies is really fruitful. And by making that available through consulting, I think we can benefit large parts of the insurance industry. So hopefully you'll hear more about that in the coming weeks and months.
That's exciting, and it's good to know with those who might be familiar with me know that I'm in the software space as well. And having just come back from the CAS annual meeting and seeing all the activity around software and what's happening with AI now, I think it's an exciting time for actuaries and for other risk professionals to be in the space. So you talked about some of the goals and some of the opportunities. I'm curious to know, whenever someone starts an entrepreneurial venture, other than just the pure opportunity, what motivated you to start something on your own? Because previously you were still doing some of this research. I think you were still tapping into those talents and exploring those opportunities with the profession. So why no? And what really gave you that push to and the conviction to move out on your own?
I think just something that's always guided me well is sometimes you have to listen to that inner voice that you have telling you, and maybe that's it sounds very unactuarial, but I think sometimes the way that we process information and we can understand which way to go, sometimes you just have to listen to those signals. So why now? I think a lot of things came together, and obviously it's not just about the evaluation of upsides and downsides in a Monte Carlo simulation. You have to also think about qualitatively, does it make sense? And just the world we live in with the amount of increasing interest and the amount of technological focus on AI, it felt right to do it at this point in time. So I'm glad that I got the opportunity, and I suppose sometimes you'll only be able to evaluate if it was the right choice down the line.
No, one more follow up on that, because insurtech obviously has been a hot topic in industry. Also, I recently attended a session on that at the CAS annual. If you were to think of your particular startup, and of course it's going to be heavily focused on AI, but is there a particular lane or sub-focus that, you know, you're going to hone in on in terms of your particular venture?
Yeah, so Dom, I think for me, something I've been very passionate about throughout my career is just how can we do things better as actuaries? What in our normal processes, whether it's reserving for liabilities or calculating capital requirements, how can we do that better, not only to provide better results for management, but also make sure that we're doing the best job that we can. And I think there's almost been a technological shift, maybe similar to the technological shift when spreadsheets came about at the beginning, I suppose, of the modern actuarial profession. I feel like today that technological shift is happening around us with better use of large language models, and these models becoming commoditized and quite cheap, or really thorough methodologies in machine learning and deep learning for things like uncertainty quantification. And because these things now exist, I think that there's a really strong business case to be made to say that we can do some of the things actuaries have always done. Those things can be done better, faster, and with better results for our stakeholders. And that's, for me, I think, a key motivating factor. I'd love to see the actuarial profession move forward and thrive in an age of AI and not get left behind. And I think that part of the work we'll be doing in the startup is making sure that every actuary's got access to some of these tools and some of this thinking.
Great. And would you say it sounds very PNC heavy? I know a lot of this discussion would be PNC heavy, but is it agnostic to line of business, or would you say it's more focused on the PNC lines?
So we definitely have a product idea in the life insurance space, actually two product ideas in the life insurance space.
Okay.
That was my first introduction to working as an actuary many years ago. And there's some elements of life insurance practice as an actuary where, again, you can apply some of these tools. So we'll definitely be looking at the life insurance space as well.
Okay, good to know. No, the first conversation that we had, I did mention you were a repeat guest. The first conversation we had was on artificial intelligence, that's AI, and machine learning, and it was more foundational in nature to help actuaries understand what the technologies are and how we could maybe begin to start using it. This conversation is going to take things a step further. But before we get into the meat of deep learning, I still do want to ask a fundamental question on AI, which I think will help us to more easily navigate the conversation. And I'll actually be looking forward to this question. So the term AI itself, it's broad, and to understand its capabilities, I think it's helpful to disentangle AI itself from traditional methods, and also to understand key differences along the AI spectrum. So how would you distinguish between the following? I'm going to mention 4 terms, which I'm sure actuaries and data scientists hear very often. So statistics, that's the first one, statistics, machine learning, deep learning, and generative AI. How do we distinguish between those 4?
Sure. So I'm going to give you my opinion, and I'll tell you how I think about it, which is quite orientated to what is the goal when you're doing a statistical analysis versus when you're building a deep learning model. And maybe as we work through the different goals and the different intentions that practitioners can have, that will help to explain the mental model I've got about how to think about this. So I think just as one caveat before we start, one has to remember that these fields are incredibly broad. So even within statistics, I'm thinking of the famous paper by 𝗘𝗏 called Two Cultures in Statistics. We can maybe provide the reference after we chat. And basically he in that discussion talks about a more data-driven approach to building models, using black boxes versus a traditional statistical modeling approach. But what's really important is he calls it two cultures in statistics. So when we say the word statistics, we're really talking about a very broad discipline that definitely has overlaps between machine learning and deep learning. So I just wanted to say that caveat just at the outset. The way I think about statistics and the way we often introduce to it as actuaries is we're talking about making inferences. Can we make an inference about, is one population mean different from another population mean? What's the best way of making those inferences? Is it by building a linear regression model? Is it by running a randomized controlled trial? There's all these different techniques that we have around making inferences about things we might care about in the world. And that's really, for me, something that distinguishes statistics from the other disciplines that we're going to briefly discuss. That's very foundational in the history of statistics. It's about making inferences. Machine learning, I think, has got a very different approach, where the primary goal of machine learning as a field, more or less to me, seems to be making good predictions. It's either that you've got a lot of previous outcomes of a particular process. That process could be, how does a P&C policy develop? Or what sort of claims arise on a motor coverage? And as long as you've got a lot of data, the machine learning approach basically says, let's take that data and using some sort of algorithm, come up with predictions. So the key distinguishing idea between inferential statistics, like I described, and machine learning is, one's a field focused on inference and another one's focused on prediction. You can also try use your inferential models for prediction. Sometimes you find out they're not so good. I remember reading a blog post a few weeks ago about how someone tried a Kaggle competition using his generalized additive models from his statistics background and was quite disappointed when they didn't perform particularly well at prediction. So I think understanding the goal and understanding the tools that arise as a result of working towards that goal is really important. Let's move on to the next rung of the hierarchy, right? So what distinguishes deep learning from machine learning? In my mind, deep learning is really all around this concept of representation learning. How can you get an algorithm to gain some sort of understanding, or in a very narrow sense, cognition about the world? So when you think about a classical deep learning algorithm, like a convolutional neural network applied to images, what that network is able to do when you feed an image in is come up with a hierarchy of concepts and say, okay, this is a picture of something that looks like a four-legged animal as opposed to a four-legged table, right? And it builds this hierarchy of things with a certain sense of semantic meaning. So that's what distinguishes deep learning from machine learning for me. It's that idea of building up a cognitive representation of the data that you give it. And then finally, generative AI, in my mind, is a subset of deep learning, or at least it is today. The whole idea of generative AI is you can take deep learning as a discipline, but instead of making a prediction, you can predict parameters of a probability distribution. So let's think a little bit about a large language model like ChatGPT. What it's doing is you giving it a prompt, which you can think of as your covariates or your rating factors if you want to use a pricing actuaries terminology. And what it's doing is predicting a probability distribution to say, what's the most likely next word that's going to come up in the sentence? And then you sample that word and you put it back. So what generative AI is all about, it's a deep learning model that's predicting distributions as opposed to just making single predictions like point estimates. So Dom, yeah, happy to take your feedback, but that's how I think about what is each of these disciplines trying to accomplish and do. And for me, that's what leads to the distinguishing characteristics.
That's very helpful. And there's something, a subset of that I want to discuss. You talked about the fact that statistics sometimes overlaps with machine learning. And speaking of that overlap, generalized linear models, GLMs, in my opinion, in my humble opinion, they're somewhat ambiguous.
Yeah.
When oftentimes I'll see articles contrasting GLMs with machine learning models, and on the surface, that seems like a viable comparison, because GLMs, they have a closed form. They're closed form multiplicative solutions predicated on distributional assumptions. So, for instance, you may fit a frequency model using a Poisson distribution, a severity distribution using Pareto, or size of loss distribution. And at the same time, they can be treated in a similar, or they're oftentimes treated in a similar fashion to a machine learning model in terms of how they're trained. So one question I'll put to you is that, are GLMs themselves considered statistical models, or AI/machine learning models?
Yeah. So I would say that it would be, at least using the categorization that I've given you before, it would be very difficult to construe GLMs, even regularized GLMs, as AI, unless your marketing team is in overdrive. And the reason for that is there's no concept of representation learning in GLMs, except at a very basic level. So for me, that rules out the possibility of them being AI. Let's talk about the distinction between statistics and machine learning. I think you can build a GLM using a very classical statistical mindset, where you perhaps have a set of data and you want to build a model to perhaps investigate different causes of claim. So what you do is you use all your data, you fit a GLM without regularization, and you might look at p-values, for example, to say, well, are some of these coefficients significant or not? And on that basis, that's how you're going to build your model. That's a very statistical way of doing it. You can take exactly the same model form, which would be a bunch of covariates multiplied by coefficients, and that gives you an outcome. And you can take a completely different lens. Instead of using all your data, you might decide to use cross-validation, or you might decide to split your data into a learning set and a test set. And that enables you to measure how well is this model going to predict. Because if we remember, the whole point of machine learning is generally as a field is to make good predictions, right? You might regularize that model and aggressively remove coefficients that don't add to the predictive capability of the model. So I think a GLM is just a model methodology, but what you use it for determines whether or not you're thinking more about a statistical application, or if you're thinking about a machine learning application, which is prediction. So I think it's both, and maybe that's what leads to some of the ambiguity. I think something very interesting from an actuarial perspective is when we started out using regression models, probably the field of machine learning wasn't as developed. So I think people took quite a statistical perspective on these models, and that's now turning into much more of a machine learning focused with really the same model form. And again, I think that's an evolution that's happening in the actuarial profession.
Excellent. That's very helpful. Something I want to ask, because I know you're in this space and you're pushing the application of artificial intelligence, machine learning, etc., to actuarial practice. Now, something is important, certainly that I see in the software space, is you get exposed to the idea of deployment. So it's one thing to build and to develop a model. But what you find, at least what I've found in practice, is that a large percentage of the models that are developed are not ultimately deployed in production. So from your perspective, I mean, I'm in the US, I'm primarily focused on this side of the world. In your side of the world, whether it's the UK, Africa, some of those geographies, what are you seeing regarding adoption and deployment of machine learning models, and deep learning models, quite frankly?
So I think deep learning, there is a lot of interest. I think there's a lot of academic interest. I don't think it's yet at the stage where there's good systems for deployment, at least in the actuarial world. So I think that holds back a little bit of the adoption, at least in the part of the world that I'm in. I think if you talk about more traditional GLM style models, yeah, a lot of models get built, only some get deployed, and only some of the ones that are deployed are ever monitored and checked after that. I think that happy middle is the machine learning space. Lots of companies have deployed GBMs in practice. GBMs being generalized boosting machines, which are a great technology and a great machine learning approach for predictions with tabular data. I think some companies just run on GBMs these days and have completely given up on GLMs. I think other companies are taking a more cautious approach to perhaps upgrading some of their GLMs to GBMs where that might make sense. Sorry, I gave the wrong, I was thinking of generalized linear models. It's gradient boosting machines, not generalized boosting machines.
Yes.
So yeah, I hope it helps. What are you seeing in the States and around deployment of particular model classes?
I mean, I think there's a couple of considerations, because the first thing you have to think of is line of business. So within property and casualty, of course, the personal line space is a little bit more highly regulated. And what's interesting is that, and I just actually getting back from the CAS annual meeting we actually did have a roundtable with someone from the Connecticut Department of Insurance, who's actually involved with the NAIC and some committees there. And he's saying that, like, one of the questions I asked is, are you seeing more submissions for tree-based and more advanced models, things that are not outside of the realm of GLMs? And he's saying yes, that there's an uptick. So certainly there is an increased appetite, and also with myself working in the software space, certainly interest in at least exploring them. I will say that companies appear to be moving cautiously. They're not necessarily saying, okay, oh, this is great, let's run with it. You know, there's a lot of change management around that. So I would say that at best it's cautious in terms of adoption. Deployment itself, I think that's another question, which might be a little bit harder to answer. I still do think that the majority of those models are not necessarily deployed. There are also some that, if they're not used directly, for instance, in the personal line space, if they're not used directly for a rating plan, they may be used as an internal benchmark as well. So that's another way that companies will use some of the more advanced models if they're not filed, if they have to be. So hopefully
I
that
think
answers the question.
absolutely, yeah. So maybe I can make one comment, and I think there's an inherent conservatism within the insurance industry. There's a lot of money at risk, and generally it's preferable to do things that have always worked. And it's only, for example, even if you think about distressed risks or the more specialized motor writers for people who otherwise can't get coverage with normal insurers, there's a certain way of doing things, and that permeates the industry because it's worked for so long. So I think that natural inclination to being conservative with new technologies is a good thing, as long as it doesn't lead to suboptimal outcomes, whether for policyholders or shareholders as well.
Yeah, and I think I genuinely think that in time, I mean, a couple of things I want to say, which hopefully will come through the course of the episode, is that when it comes to the more advanced models, it's not just as simple displacing some of the older models. So there may be cases where the GLM may be more appropriate, possibly because it's easier explainable, because the scope is more narrow in terms of whether it's the line of business or the context. Maybe it's sufficient to have that explanatory power that you need. So I think that's something else that's important to note as well, is that it's like with any kind of technology or tool software, is that, for instance, Microsoft Excel is still around. There's more advanced software, but Excel still holds its own with things of a certain scope. So I think I always like to take that very nuanced approach to the technology and to software.
Agreed.
No, I did mention the theme of today's discussion is deep learning. So let's get into a little bit deeper into this, no pun intended, into the topic. So one of the most common deep learning models is neural networks. I think you might have spoken about one of them maybe briefly earlier, but let's recap that. How do you describe a neural net? If we were to talk about neural nets, just how do you describe that particular type of deep learning model?
So, Dom, just coming back to that concept I mentioned before of representation learning, where a model comes up with its own almost cognitive representation of the data that it's understanding, in inverted commas. That's really what neural nets exhibit. Neural nets are one of the most classical algorithms that exhibit this property of representation learning. And the way that neural nets do this is almost by coming up with their own description of the input data. So a nice way of thinking about neural nets, just to describe them, is think of them as many GLMs or many regression models stacked on top of each other. And the earlier ones in that stack that are closer to the data, what they're doing is they taking in the input data and coming up with a new representation that's optimal for making predictions with. So let's say you're talking again in the pricing context. If you think about when you build a GLM, you might have an interaction between past number of claims in the 5 years and the age of the driver. If you're going to build a GLM, you have to specify that manually. But something that neural nets excel at is finding those corresponding variables where you need to amplify in the presence of both of them, or almost downweight sometimes if needed. And that's really what a neural net is. Like I said, it's just layers of regressions that are stacked together to come up with its own representation of what's important in the input data. And then it's effectively just a GLM on top of those new variables that the model has learned in order to make the predictions. Often you'll see those diagrams. I'm sure if I mention it, a lot of your listeners will be aware of them, is with all of those circles which represent variables, and then those connecting lines which represent regression weights. And really what that diagram is just a diagram of stacked regression models. So hopefully that helps a little bit.
That helps. And I've seen the diagrams, and at the first time that you look at them, it can be a bit daunting, but I imagine with a little bit of study, it starts to make more sense.
Absolutely.
Something that we mentioned too in the pre-meet, I'd heard this before, not from first-hand experience, but just from people who have worked with these types of models, is in the past, neural nets themselves have been criticized for being over-parameterized. So what precautions can be taken to reduce the risk of overparameterization for neural nets?
Absolutely. Let me say a few things about that. So firstly, what is overparameterization? It's very much a concept that started in statistics, where if you're aiming for a simpler and more parsimonious model, you try not to increase the number of variables that you might have. So let's say you've got 15 input variables. You probably, in a normal linear regression, don't want to take the interaction of each of those variables together. You'll get a very large number of variables going into your model, and that is what we'd classically call overparameterized. I think something that the first generations of neural nets suffered from was this idea of overparameterization. And when I talk about generations of neural nets, if I remember my history, we're actually on something like the third generation of neural nets now. You had your very first ones in the 1950s called perceptrons, which weren't really even useful for regression modeling. Your second wave of neural nets, which was probably from within the 80s and 90s, were very similar to regression models. They maybe overfitted, and you'd be very worried about the number of parameters. But in this third generation of neural nets, I think we can safely say this time is different. And the reason it's different in overparameterization is maybe less of an issue, is that we've come up with new deep learning model forms. So you're no longer using the old model forms from the 80s and 90s, those diagrams with the circles and the lines connecting them. There's all sorts of new methods of designing and fitting neural networks which inherently mitigate the overparameterization problem. And that's why you can have large language models which are based on a model architecture called the transformer, which can scale up to even hundreds of billions of parameters. And you can fit these models without necessarily overfitting. And that's because the model form itself mitigates overparameterization and mitigates the downside consequences of overparameterization, which are, hey, your predictions just won't be particularly good. Maybe also just to mention that besides for the unique architectures which have now been developed and are easily available with 3 or 4 lines of Python code these days, another thing is a whole range of regularization techniques. So we've mentioned this concept of regularization in this discussion, but basically it's a way of modifying the fitting process of coefficients in a statistical and machine learning model. And there's very highly effective regularization methods that are available for deep learning. So I'd say a concern around overparameterization is 100% valid if you're dealing with the simplest neural networks that you might come across today. But as these things get more advanced and you're layering in all the modern advances, that kind of vanishes and goes away.
That's helpful. So it sounds like there's been some evolution. The form has evolved a bit, and you know, that challenge is being commonly addressed.
So Dom, if I could make one suggestion, if any of your listeners are interested, there's a fantastic paper called Dropout by Geoffrey Hinton and a few of his co-authors. And Dropout has become one of the leading methods for avoiding overparameterized neural networks, and has actually got some very nice analogies in the paper as to why the technique works. So if I can recommend that to anyone who's looking for some weekend reading, that can be a fun place to start.
Excellent. So when we talk about neural nets and deep learning, you know, coming back to the beginning of the conversation and some of the things I mentioned around adoption, deployment, and in the bigger picture, what you're trying to do with being able to apply some of these techniques, these more modern techniques, to actuarial practice. There's 3 trade-offs that I typically think of when we go to a more advanced model beyond, say, the GLM. There's accuracy, of course, the potential for the model to be more accurate. There's a complexity, of course. With more accuracy could come complexity, looking at when you start to incorporate non-linear relationships, for example, and then also the explainability. I guess those two go hand in hand. Explainability to internal stakeholders, regulators, etc. So when you think of deep learning models, not necessarily limited to neural nets, but when you think of that trade-off between the accuracy, the complexity, and the explainability, how do you think of that trade-off? Because I know sometimes they're marketed, and even me being in the software space, when I think of machine learning models, sometimes I have to be a bit more nuanced in terms of how I discuss them, because I don't want to promise just guaranteed more accuracy. I know that there's a trade-off there. So thoughts on those 3 things?
So can I add one extra dimension? Now we're working in a 4-dimensional space, which is speed of production.
Okay.
I think is another interesting one. So let's just run through yours and then maybe we can mention mine very briefly. I do think a lot of research and a lot of my own practice has shown that machine and deep learning models do outperform on an out of sample basis if you compare them to GLMs. What you can do, so I think on that dimension of the trade-offs, you can get greater accuracy with these models. Of course, you can take some of the lessons as to what's driving that greater accuracy and go back and enhance your GLM model, which is also a possibility. So also important to say they're not completely orthogonal. If you've got a really well-performing machine learning model that can then inspire you to make some changes to your GLM, that can also be a really powerful methodology. I think a lot of machine learning models, without a doubt, are more complex. And the way you can maybe think about complexity is, can you reason and rationalize your way through just what is this model doing? And generally, to hold in your head all the different bits of a deep learning model is extremely difficult. Whereas a GLM, more or less, it's a linear model form. You can look at the coefficients and more or less work out what's going on. So I think you're absolutely right that machine and deep learning models have that increased complexity. Explainability is an interesting one because it's quite easy to take machine and deep learning models and modify them so that they become inherently explainable. So in the past few years, together with 𝗪𝗏 and some other co-authors, we've come up with this idea of what we call the local GLM net, which creates a GLM for every particular policy that you're making a prediction for. And in that case, you've got almost perfect explainability. So maybe it's a little less clear that machine and deep learning models are less explainable. And I'll make a counterpoint that I often make to people in the other direction, which is, how explainable are GLMs? And there's two components to that. Let's say you've got a 50 variable GLM for personal lines pricing. Just understanding the impact of those 50 variables and holding them in your mind at once is not as easy as if you've got 4 or 5 rating factors, right? And another component is that one has to remember, when you fit a GLM, you're not getting marginal effects. So if you're looking at a one-way analysis in pricing, which is what is the relationship between claims frequency and age, you often see a decline from younger ages into middle ages. That may very well not be there just because you've got different variables which are correlated with each other. So you're no longer looking at marginal effects. And I'd argue that we're not that good at really understanding marginal effects in GLMs either. And then the last dimension, the one that I added, is just around efficiency and how quickly it takes to produce a highly accurate model. And I think in that case, the machine and deep learning models clearly win, because to build a really good GLM by hand, the old way that actuaries have always done it, that can take an extremely long time. And you can be sitting there for 3 months playing around with different combinations of variables, where if you have your fitting routines sorted out, you can fit a deep learning model in maybe a minute or 2 minutes. So I think, exactly as you said, there's a number of trade-offs, and it really depends what are you aiming for. If you're in a market where accuracy doesn't matter and you have to do a rate filing explaining the rational expectations of why your coefficients look the way they do, probably a deep neural network is not the right answer. But if accuracy really matters and you need to get something out quickly, a well-tuned GBM training pipeline might be what you're after. And I think being open and transparent about what your models can do and what the various different model classes, how they lie in that set of trade-offs, I think is really important.
That's very helpful. Just one more thing I'll add is the reason I brought up the accuracy. I remember one, and bear in mind, I was not the one who developed this model. An actuary once told me about a model. It was developed, I think, in Python, one of the open source languages, around to come up with reserving indications. And I think it came up with an answer of a range, of 0 to 1 billion. And I was thinking, okay, well, that's not very helpful, something with that much variance and variability. So it's just something I thought of because,
Yeah, I think the one thing that's clear is, and maybe this is what I was emphasizing before, you have to have a good model fitting pipeline, because you can get really poor results from machine and deep learning models if they're not fit properly. So just because you're using a popular open source library like XGBoost in a nice open source language like R, if you're not doing it right, you're going to get results that are not particularly impressive. And I think that's exactly what you're pointing to is you can produce really poor results with machine and deep learning. Whether or not it's harder to do that than with GLMs is maybe a conversation for a different day.
Yeah, that's helpful. And one of the things I want to shift gears to know is I want to start to discuss some of the takeaways from your papers. And I think this is a great opportunity because some of the papers that you write, they're very technical and they have some very great insights. And I think we have a good opportunity to just get straight to the source, speaking to the author and be able to understand the value in those. So one of your recent papers discusses smoothness and monotonicity constraints for neural nets using ICE-net, the individual conditional expectation. So first thing is, like, what was your motivation for writing this paper?
Yeah, so Dom, it's a nice place to start. So I think what we've accumulated over the years in the actuarial profession is a set of desirable characteristics for actuarial models. Often we know that certain relationships should be monotonic. So for example, if a person's had a significant number of claims in the past, that's generally a good predictor of the number of claims on a personal lines policy that they'll have going into the future. And you generally want that relationship to be monotonic. What do we mean by monotonic? If you've had more claims in the past, your prediction should increase, shouldn't decrease, right? So that's one sort of a desirable characteristic that you might want for models. Another desirable characteristic that you often find more in life insurance practice is the idea of smoothness. So in life insurance practice, when you derive mortality rates from a set of data, often you've got a whole bunch of noise that you don't really believe is there. You might think the reason that you've got all of this noise is just because you don't have enough data. So what life actuaries will generally do is smooth out or graduate those mortality tables. So what the point of this paper using the ICE-net is how can we incorporate some of these desirable characteristics into neural net modeling? And that's really what the whole idea was. Important to say, with things like GLMs and GBMs, you can impose monotonicity constraints quite easily. You can smooth GLMs, but you can't smooth GBMs yet. So what I try to do in this paper was give neural nets the best of all characteristics by coming up with a general methodology for enforcing any sort of constraint that you'd like on the outputs of a neural network.
No, regarding the ICE-net, individual, correct me if I'm saying it's wrong, conditional expectation,
Perfect.
just what does that, just to for those of us who may not be familiar with that expression, what is that and why was that the technique that you used?
There's this whole field around post hoc explanations of black box models. So if you're working in the field, you may have heard of SHAP, which is a very nice technique for doing that, but it's a little bit more complex. All an individual conditional expectation is let's say you pick a particular personal lines policy that you've got a pricing model for, and you want to understand how does the model behave as you increment up or down one of the variables. So let's say you start off with a driver who's 18. What's the minimum driving age in the state? 16. Okay, so let's go with someone who's 16. You might want to say, as they go from 16 to 17, 18, 19, 20, all the way up to old age, what will the premium that you give them be? How's that premium going to change with that particular variable? So there's a very obvious and simple intuitive model interpretability analysis that you can do. And the whole idea that we took in this ICE-net paper is when you're training an ICE-net, in addition to making predictions, you also make predictions across all of those variable dimensions, like we've just mentioned, perhaps age, and make sure that the predictions all relate to each other in a sensible way. So it's actually a really simple idea. There's quite a lot of code that you need to implement that, but the results are actually quite nice. You can now smooth out and enforce monotonicity on neural nets in a very intuitive and, I hope, appealing way that talks to the sort of analysis you might perform on a model anyway.
So it sounds like, if I'm getting this right, the key takeaways are more using that particular technique to impose the smoothness and monotonicity to essentially improve the results regarding to be able to achieve smoothness and to get monotonicity where you may have variables jumping around, as it kind of when they should be going in one direction. Would that be fair to say?
That's a brilliant summary. And maybe the other interesting thing that one can say is that it's not just about good actuarial modeling practice. often if you've got model variables in your model that jump around quite a lot, you can upset all sorts of stakeholders, most importantly your policyholders. So there may be some variables where just for commercial reasons you want to impose that sort of smoothing or otherwise sensible relationship. So I hope this idea of the ICE net or the ICE net can allow actuaries to use neural nets in a way that is both more actuarially but also commercially appealing.
Yeah, that's helpful, and I hope folks take the time to read these papers, this paper and a couple of others that we'll discuss. So continuing the conversation on deep learning, applying classic actuarial concepts to deep learning, that's something that you've experimented with in recent years. That's not just the topic of this episode, but you don't have to research on this. So taking a step back, what does actuarial deep learning look like? If now we're combining concept of deep learning with actuarial practice, if you coin that expression, actuarial deep learning, what does that look like to you?
So Dom, I really like that term, and I might borrow it if I may as well. I think a lot of what one has to be aware of when you start getting into this actuarial data science field is that most of these models were developed outside of insurance. Insurance isn't the primary it doesn't occupy a primary place in the thinking of the people developing these models. So for that reason, a lot of the things that we need, particularly within actuarial practice, just hasn't been accounted for. So we've just spoken about smoothness and monotonicity. There's also a positive aspect to it that over many years of actuarial practice, we've kind of figured out how do you build good models in insurance markets. And an example of that might be the idea of credibility. Just because you've got one policy with a particular amount of claims experience, don't give that data point full credibility. Look at a wider portfolio and blend between different sources of information. So I think the way I describe actuarial deep learning is how can you bring in all of these good ideas and good practices that have been developed within the actuarial discipline, and how can you apply them within this fantastic new modern technology that we've basically all got access to? It's bringing together the good parts of both and making sure that the models that you produce are fit for purpose if you want to deploy them for actuarial purposes.
Now, I'm glad that you mentioned credibility, because we're talking about classical actuarial concepts and how you blend those with deep learning models. And that brings me to your next paper. Yeah, I know you have several papers, but we're primarily going to touch on 3 in this episode. The second paper, the credibility transformer, and I'm quoting from the paper itself. You demonstrate a novel credibility mechanism which leads to predictive models that are superior to state-of-the-art deep learning models. That's what you claim in the paper itself. So two questions I have is, what is a credibility transformer and how does it enhance deep learning models?
So let's start with what transformer models are. So transformers are probably the most important model class within deep learning. They were developed in a 2017 paper called Attention is All You Need by a bunch of researchers at Google. The lead author's surname is Vaswani. And basically this technology now underlies all of the large language models that you see out in practice. It's all a bunch of transformer models, maybe amplified and made bigger than the original one, but that's what a transformer model is. And the insight that we had when you look closely at the structure of a transformer model is that you can actually restructure the model to take account of credibility between two things. And those two things are, what are an individual set of policy characteristics? So if you're talking again in the pricing context, it might be past claims history, age of the driver, where they live, etc., versus what is the overall portfolio experience. So if you think of your classic credibility formula, it's generally a blend between a more individual set of experience and a portfolio set of experience. And what we were able to show is that if you structure your transformer right, you can actually have your transformer perform that credibility calculation for you, which is a blend between a portfolio's experience and then individual model experience. And what do we mean that it actually enhances state-of-the-art transformer models? So we took an open source data set and we fit a very complex deep learning model, transformer, to it, using all of the tricks of the trade from the large language model world. I'm not going to go into those in too much detail, but basically all of the good modeling practice that has developed since that 2017 paper on transformers. And what we found is that, okay, just fitting one of these models does lead to quite accurate results, but applying this credibility mechanism within the transformer even improves over those. And in some instances, the jump in improvement in accuracy is similar to the difference between a simple neural net and a GLM. So quite significant. And that's really what we showed in that paper. So for me, that's almost become a case study that I like to cite about how you can bring traditional actuarial thinking, and there's nothing more traditional than credibility theory, into the latest cutting edge models. And a good reason for doing it is not only that you can then get actuarial stakeholders to understand what's happening in a much more intuitive and foundational way, you can actually get real boosts in predictive accuracy from doing that.
Now, what was the reception for that? Are you seeing people? I know the paper I think it's fairly recent, at least within the past year or so. Are you familiar with anyone who's tried to implement that in practice?
So we will be releasing some open source code to allow people to implement that in Python.
Okay.
So people can try it out. And next week I'll be presenting it at the Actuarial Society of South Africa's annual convention. So I hope that there'll be some interesting feedback from participants, but it has been received quite well, particularly by some audiences in South Korea and Japan.
That's excellent. And I think that's the essence of this episode. It's not just, even though the theme is deep learning, it's not just about deep learning, because like you said, deep learning in a vacuum is a concept or a construct that may or may not be relevant to actuaries without that broader insurance and risk management concept. So I like that blend of actuarial theory with deep learning. That's what we're trying to get at in this episode.
Yeah. Absolutely.
Now, to the third and final paper that we're going to discuss today, something that certainly is near and dear to the Maverick brand is the actuarial profession itself. You recently published an AI vision for the actuarial profession for the CASE forum. So what can the actuarial profession do to capitalize on this era of nets and generative AI?
Yeah, I think there were a few main points I try to make in that paper, and maybe it's more accurately called a manifesto. I think the one is that we should embrace AI in the actuarial profession. We've got this fantastic history and legacy of deep knowledge of finance, of statistics, and there's no reason to be averse to a new technology which may do certain things we've done classically that may allow us to do those same things better. So I think one thing I'm trying to advocate for in that paper is let's be AI friendly. And let's look at it not so much as a threat, but as an opportunity to enhance what we've always done. And if we take this concept of actuarial deep learning, or what I call in the paper the AI enhanced actuary, the vision that I have and what I hope the profession will respond to is that we blend the best parts of what the actuarial profession has always been with the opportunities and new technologies enabled by deep learning. That's really what it's about. And I think if I summarize the point that I make in that paper, I think we stand today at a little bit of a crossroads. So we either can embrace this new technology and become leaders in our traditional fields of whether it's insurance or investments or pensions, and maybe we can even go outside of our traditional fields as we build our deep professional expertise with these models. Or I suppose there's a downside scenario where we don't jump on the wave with our surfboard and surf, and the opportunity passes us by. And instead of an AI enhanced profession, we may be competing with other professionals using AI. So again, what I'm advocating for is I think we need to seize the upside, because there's also some significant downside costs of not doing that. And really the vision is one of blending AI with the traditional principles, practices, and the legacy that we have as being part of a great old historic profession.
I love the vision, and I think you use the term AI enhanced actuary, which I think is very simple and encapsulates what you just said. It's blending the two. I have a couple of follow-ups. When I was reading through the paper, I noticed a few things. One is you talked about reserving, and you talked about an actual versus expected analysis that would typically be accompany a reserve review, and you talked about, I guess, using AI to augment that and come up with observations. And the first thing that came to my mind is, thinking of actuaries, reserving actuaries who've done that for several decades. Just curious to know, maybe we have not enough time to observe this, but what do you think the reception to that thought process is? Because that's just something that I know has been bread and butter for reserving actuaries. Do you feel like
Yeah.
they're going to feel like their territory is being encroached on?
Yeah, I mean, I think reserving actuaries, a large part of my career has been in reserving. I think a couple of interesting things. I think reserving actuaries are under immense stress and pressure as the demands on them increase, perhaps particularly outside the US. So you've had the introduction of Solvency II, so you have to perform a cut of reserves in your Solvency II classes of business using the Solvency II specification. At the same time, if you are in an IFRS 17 compliant jurisdiction, you also then need to perform a cut of IFRS 17 compliant reserves. So more and more is being asked of your actuaries. On the one hand, and at the same time, better data is becoming available. You might now be able to reserve a motor book by peril, or you might reserve for different states instead of just doing one overall reserving triangle. So the overwhelming feeling I see among reserving actuaries that I deal with is people know they have to do more, but they don't really have the time or resources to do it. I think that's exactly where AI can plug in. Instead of you having to puzzle over reserving AVE analyses coming from 50 lines of business and work out which accident year problems are coming from, if you've got a trustworthy AI system that can immediately pinpoint which lines of business have got a problem, which accident years it's coming from, and draw the parallels among lines of business. So, for example, is there an issue of social inflation, or is there a particular issue with claim severity in several lines? That can immediately put you in a position where you understand what's happening in your triangles much faster than you otherwise could have. So again, I think it comes down to what's our attitude. Is it about let's enhance the great work we've always done? Or is it around, okay, the machines are taking over? And I hope and I think our attitude should very much be the former rather than the latter.
Yeah, and I fully agree, and agree with the thought process. I do certainly think, and it's not necessarily a bad thing, I think that when we have these types of changes, like you said, you talked about the vision of using AI to speed up some of these observations so you don't have to spend the time going through the triangles or, you know, but I think in reality, you're going to have, I think there's going to be folks who may be exposed because perhaps that's the way they've always done things. That's what they were focused on. And you may find that there are some folks who were spending the majority of their time doing some of the things that AI can now do. So I think certainly, I think even though I think that will be not necessarily the majority of folks, that will be certainly some. And a second thing I wanted to ask about is regarding, I think you mentioned this, you talked about if in the event that we don't embrace it, now you have people in data science, people who may not have the domain knowledge, people who, or maybe they do, maybe have some domain knowledge, and they're unconstrained by the requirements of professional guidance or regulation. I think this one is interesting because I really do think, and this topic I think came up several times in the annual meeting, is that that's really where I think actuaries add the value is a context around the modeling. I think you can have the most sophisticated techniques, but if you don't have the right context for the models themselves, I think that's where actuaries add a lot of the value. Being able to put it in the context of the domain and in the context of the business and the decisions. So that's an opinion, I guess, that I share. I don't think it would necessarily be as simple as if actuaries were not to embrace it, them being unilaterally displaced. I think there could still be some displacement, but I think it's one thing. Yeah, go ahead. Sorry.
I think what's interesting about that is actuaries are great at providing the industry knowledge and the context for models. But if management finds that some of the data scientists down the corridors are making more money using more advanced models, that's when you're going to have a real commercial consideration. And the softer value add that actuaries can currently bring may not be enough. So I'd very much like to see a future where actuaries are the best modelers in the insurance domain, as well as being able to provide that full overlay of the professionalism, of the ethical perspective, and the business context. And I don't think that there's any reason why we can't do that. maybe it's just an extra course you need to take, or it's an extra curriculum to go through. And I think that's, again, part of the peril versus the opportunity here. If the opportunity is seized, you can have actuaries being the preeminent modelers in the insurance domain, and perhaps even extend outside. But if not, and other modeling professionals can do a better job, the commercials might lead to a different outcome. So yeah, I think that's exactly the upside and the downside scenario.
Excellent. Well, if I were to recap that what we talked about today, we had a great opportunity to talk about from the fundamentals of AI, look at that, how statistics differs from machine learning and deep learning, and understand that spectrum of AI. We talked about deep learning and using neural nets, which is one of the most common examples, describing what that is. Talked about some of the ways of addressing the overparameterization. We spoke about a few of your papers, which were specifically applying either applying actuarial concepts or addressing very specific things that actuaries would contend with through the context of deep learning. And then we close with a vision for the future. So I can't think of a better, few episodes have been, I think, more valuable than this. And I love the cutting edge episodes where we're looking at things, where we're being forward thinking of talking about these cutting edge topics and being able to share that with the community. Not just share it, but share it in a very succinct, meaningful way, I think is the most rewarding part of this. And just want to thank you, Ron, again for joining me a second time and sharing your expertise, and very excited for this new chapter for you and in terms of your entrepreneurial venture. And as always, let's keep in touch, and just wishing you the best as you move forward with things.
Yeah. Dom, it's always a pleasure to speak with you. I always have left inspired and looking forward to our next conversation, and keep doing the great work on your podcast. It's one of my favorites. So thank you so much.
Will do. And I hope that our next conversation is in person. I hope to get to South Africa at some point.
Absolutely. We look forward to welcoming you.
Excellent. Well, have a wonderful rest of the day, Ron. Take care.
See you, Dom. Bye-bye.
Bye-bye.